What the heck?
Tagon.
Hello there! We're finally going to do part 2, or chapter 1, of my real analysis series. I know it's been a little while since I put out the video. Stuff's been kind of going on, so I am able to focus on it now. I'd like to remind everyone that I have a Patreon now, that if you want to support my channel so that I can dedicate more time to doing this and investing more money in maybe better equipment, like a stand-up board and things like that, then feel free to go to this URL right here, which is also in the description of the video, to pledge your support. You will be mentioned at the end of the video, at the beginning if you do the highest one, and there are various other perks that come along with that, so please consider it if you want to support the channel. Thank you very much. But on to the video. So this is our first chapter of really digging into the actual concepts of real analysis. So we're going to base this entire lesson on the sort of foundational assumption, or one of the foundational assumptions that you can start with, which would be the axiom of completeness. And this idea, which I will elucidate once we start, is essentially a way of distinguishing the real numbers, which is the number line, the whole number line, from just the rational numbers, which in the last video we showed were dense in themselves, right? Because like there's always a rational number between any two different rational numbers. But we were also able to show that the square root of 2 is irrational, so it shows that there are these other numbers that aren't included in the rational numbers, and so we need to somehow account for that and distinguish that new set from the original set of the rational numbers, and that's precisely what the axiom of completeness aims to do. So let's talk about that, and we'll cover a bunch of other topics as well. Let's do it. So, I actually have to make a correction from my previous video that I made an error in. So, in the last one, when I was talking about injective and surjective functions, I said that this was an example of an injection. I think there was a 7 as well. And I did this as my example, or something to that effect. And this is ridiculous because this isn't even a function, right? And somehow the definition eluded me, and I, for some reason, gave this as an example of an injection. It's technically an injection in the sense that all of these things are hit by some element of the domain, but one element of the domain is hitting 3 different elements of the codomain, or image, or whatever the hell it's called. And so this isn't even a function, and so this was kind of a stupid example to give because it's not even an appropriate example. So what I should have done for the example of an injection was something where there was more on this side than on this side, because then I could just do this. So this is an injection because everything in the codomain is hit by some element of the domain. It's not one-to-one because 5 is hit by both elements 2 and 3. So clearly f of 2 equals f of 3, but 2 does not equal 3, so this is not one-to-one. And a one-to-one example would just be something where all the elements that do map onto something sort of do it uniquely, and then a bijection would be like if we had both of those things at one time, so we would need one more element, like so, and then this would be a bijection because everything in here hits one of these uniquely, and everything in here is hit, so this is a bijection. And so that's the correction I just wanted to make. For some reason I didn't even use a function when I was explaining properties of a particular kind of function. Silly me. Just adjust my camera there for a second. So let's cover the main topic of the video, which is going to be the axiom of completeness. So recall in the last video we were able to show that even though there was always a rational number between any two different rational numbers, there were these other numbers, despite the fact that we could always find a new rational number between any two. There are all these other numbers, potentially, that do not fall into that set of numbers, that are not rational. And we were able to show that one of them existed, and that was the square root of 2, if you recall. So let's quickly mention what it is that we're going to use, for the most part, to distinguish the real numbers from the rational numbers, and I'll show you precisely why this does not work for the rational numbers, and why this is a good axiom to have for the real numbers. So this is called the axiom of completeness. And the reason why it's called the axiom of completeness is because it allows you to fill in all of the gaps of the real numbers that aren't filled in by the rational numbers. And I'll explain exactly what I mean, but first let me give you the definition, or let me state what the axiom is. So the axiom is that every subset of the real numbers that are bounded above, and I'll underline that because that's a new phrase, bounded above, has a least upper bound. That is the axiom of completeness. Let's see what this means. So let's parse it one term at a time, right? So this says that every subset of the real numbers that is bounded above. Now what does that mean? What's a subset of the real numbers? A subset of the real numbers is a collection of numbers that are elements of the set of real numbers. So we could imagine like a set of just, 1, 2, and 3. And we'll throw 1/2 in there just for good measure, right? This is a collection of real numbers. It's also a collection of rational numbers, but the point is that this is a proper subset of the real numbers because we know that the rationals are real in the sense that they belong to this collection of numbers that we want to investigate. Notice that it's also bounded above in that there is some number that I can say that is greater than or equal to all of these things. Right? So, for example, 4 is bigger than all of these numbers, and so this is bounded above. There is a number that is bigger than everything in the set. It is bounded above. And so what we're claiming is that for any subset of the real numbers that is bounded above, which means that there's some number that's greater than every element in the set, then there is a smallest number that satisfies that requirement. There is a smallest number that is bigger than everything in the set, or equal to. So for example, the answer here would be 3, because 3 is bigger than or equal to everything in this set. And so the least upper bound of this set would be 3, because it's the smallest number that's greater than or equal to everything in the set. Moreover, because 3 is actually in the set, it is the maximum of the set, right? So we're going to also elucidate that if the least upper bound is in the set, then it is the maximum of the set. And those will actually be the same. Notice that this is also bounded below. I'm not stating bounded below and greatest lower bound because you can sort of imagine the mirror image of this axiom and it would just as equally apply. And so you want to assume as little as possible and prove everything else. But notice this is also bounded below, right? There are infinitely many numbers that are less than every element of this set. But the smallest number that is less than or equal to everything in the set is 1/2. So this would be this is the greatest lower bound, which we write as GLB, or infimum, and 3 is the least upper bound, LUP, or supremum, SUPREMUM. But in this case, because both of these things are also in the set that we're talking about, then this is also the maximum of the set. So these are the same. These are just two words for the same thing. These are the same. And then because this is the smallest element of the set, it is also the minimum of the set. So it's probably not too hard to see that the minimum and I'm just going to talk about maximums, but the minimum is just the other thing, the other option there. It's worth noting that if a set has a maximum, and we'll cover sets that don't, then it is the least upper bound of the set, which again is the smallest number that's greater than or equal to everything in the set. Because if it's the maximum of the set, then there's no element of the set that's bigger than it. So let's sort of delve into these terms a little bit more. I'm just giving you a particular example, but we can sort of get a little bit more general with it. Let's be a little bit more rigorous with our definitions. Given a set A that is a subset of the real numbers that is bounded above, by the way, if one says that a set is bounded without specifying which direction, it means that it is bounded above and below. So, but for the sake of this argument, we only need bounded above, or not argument, but definition. Given a subset of the real numbers that is bounded above, then B is an upper bound of A if B is greater than or equal to little a for all little a in big A, right? So this is just saying, this is making it more rigorous and mathematical, that a number B is an upper bound of a subset of the real numbers if that B is greater than every little a, which is an element of big A, right? So it's bigger than everything that's in A, and so that's the definition of an upper bound. A lower bound has a very similar definition. It's less or than or equal to every element of a set that is bounded below. So again, for all of the lower bound things, you can just mirror it to the other end of a set, and that's quite easy to do. So again, with the same set, S is the least upper bound or sup A for supremum, and I'm going to be using this one more often than anything else, and infimum for the lower one as opposed to GLB for greatest lower bound. So S is the least upper bound or supremum of A if S is an upper bound of A. So this is requirement 1. If S is an upper bound of A, and 2, if S is less than or equal to B for all upper bounds little b of A. So what this is saying is that if S is an upper bound of A, and S is less than or equal to every other upper bound of A, then S is the least upper bound of A. It's not too hard to see, right? Okay, and then one final definition. Again, this is easily transferable to the greatest lower bound of a set. So M is the maximum of that set A if M, again, the two requirements, if 1, M is in A, and 2, M is greater than or equal to all little a, little a for all little a that are in big A. So notice that the maximum is something that's in the set and bigger than everything else. The least upper bound is something that is just an upper bound of the set and less than or equal to all the other upper bounds. So we're going to show that if a set has a maximum, then that maximum is the least upper bound. And it's not too hard to do that, because notice M is greater than or equal to every element of A, right? Which makes it an upper bound, correct? And because it's also in the set, any other upper bound of the set has to be outside of the set. Because if it were in the set, then M wouldn't be the maximum. So all the other upper bounds have to be above the set, greater than anything in the set, greater than, in particular, the max of A, which means that the maximum of A, if it exists, is the least upper bound of the set A, and it has to be. And you may be thinking, what do you mean if a maximum exists? Doesn't a maximum always exist? And no, a maximum does not always exist. Because imagine we had the set from 0 to 1, right? The maximum exists in this case because this is a closed interval, right? We are including everything between 0 and 1, including 0 and 1, everything, even the endpoints. But if I do the open interval from 0 to 1, now there is no maximum of this set, because 1 is not in here, but 0.9 is, and 0.99 is, and 0.999 is, and I can just keep adding 9s. And even though I'm adding progressively smaller amounts, I'm always getting bigger numbers. And since 1 isn't there to cap everything, that means there is no maximum in this set. But I don't think it's too hard to see that the least upper bound of both of these sets is still 1, right? Because 1 is greater than every element in here, and it's also the smallest number that's greater than everything in here. And in particular for the first set, it actually is in the set. It is the end point of the set, the final element. And so it is the maximum of the set, which by definition makes it the least upper bound. So I hope these definitions are clear so far. We're going to be using them pretty freely, so make sure you understand what they mean. So we're going to do a little bit of a reframing. We're going to assume that my little glossing over explanation of the maximum is a good enough proof that if you have a maximum, then it's the least upper bound. We're going to sort of rephrase what it means to be the least upper bound now. And we're going to utilize the same epsilon tactic that we did in the first video when we showed that two numbers are equal if and only if their difference is less than every positive number, right? So let's utilize that again. So we're going to take a set A, which is I said an element, which is a subset of the real numbers, right? With upper bound S. So this is a set that is bounded above, and it has an upper bound S. So S is the supremum of A, in other words, the least upper bound, if and only if what? If and only if for all epsilon greater than 0, we have that S minus epsilon, so is less than little a, for some little a in big A. So let's parse what this says. We're saying that we are given a subset of the real numbers, and that is bounded above with an upper bound of S. We are then saying that S is the least upper bound of A, if and only if, for every positive number. If we took it away from S, we would end up with something that is less than some element of A. In other words, if we take anything away from S, this is no longer an upper bound because it's less than some element, which means it can't be an upper bound of A because some part of A is bigger than it, so it's not an upper bound anymore. And so, because this is an if and only if statement, we have to prove it in both directions. So, we're going to first assume that S is the least upper bound of A, and then we're going to prove it in this direction and prove it in the other direction. So first we're going to prove this direction. So S is the least upper bound of A. That means it's less than every other upper bound of A, right? It's less than all of them. And it's not very hard to see why this has to be the case. If S minus epsilon were greater than or equal to A, or more precisely, not less than A, then S minus epsilon would be an upper bound of A, which is smaller than the least upper bound, right? Which doesn't make any sense. We assumed epsilon is positive, so subtracting it away from S gives us a smaller number. If it's still greater than or equal to A for all A inside of big A, then we have a new least upper bound, right? It has to be less than some A, because if it wasn't, we would have a lower least upper bound, which goes against the assumption that we made at the beginning, that S is the least upper bound. So this is, so therefore, S minus epsilon is less than A for some A in A, big A, for all epsilon greater than 0. So that proves that direction. I hope that's clear. So let me just say that one more time. So essentially what we're doing is we're assuming that S is the least upper bound, and then we're proving the next part. We can prove the next part by simply investigating what it would be for it not to be true. Right? We want to show that if S is the least upper bound, then no matter what positive number I pick, positive real number, S minus that positive real number will give me a number that is less than some element of the set for which S is the least upper bound. And that's got to be the case, because if S minus epsilon were greater than or equal to all elements of big A, I should have said that there, but I'm saying this is all elements, because we only need a single element for it to not work. So this is saying that this has to be greater than or equal to all elements. If it was, then this S minus epsilon, which is smaller than S, would be a new upper bound of A, which is less than the least upper bound, which doesn't make any sense, right? So that would be a contradiction. Therefore, it has to be the case that for every positive number epsilon, the least upper bound minus that number is less than some element of the set. So now we have to prove it in the other direction, right? So we're going to assume that for all epsilon greater than 0, this is true. For the upper bound S, right? We're going to then prove that that means that it has to be the least upper bound if that's true. So we're going to assume that for all epsilon greater than 0, S minus epsilon is less than A for some little a in big A, right? We know this is our main assumption, that S is an upper bound of A. So we still have the fact that it's an upper bound. We're just now going to prove that given this assumption, S must be the least upper bound. And again, this will not be too hard. What is the requirement for S being a least upper bound? So we already know it's an upper bound. That's the first requirement. The second requirement is that it has to be less than or equal to every other upper bound. So for the sake of the other direction, we have to assume the second part of the proof and then prove that the first part is the case. So we're assuming that for all positive epsilon, taking that number away from S results in a number that is less than some element of big A. So if this is the case, then if there exists some number B, which is less than S, then B is not an upper bound of A. I know that this is the case because if B is less than S, then S minus B is positive. So I can take epsilon to be S minus B because it can be any positive number I want. So I can clearly check that S minus the quantity S minus B, which gives me B, is less than A, some A inside of big A, right? Which means that B can't be an upper bound of big A because it's less than some element of A, right? Just by picking epsilon to be this positive number S minus B. That means, then, therefore, if B is an upper bound of A, then B must be greater than or equal to S, which implies that S is the supremum of A. And let's go through that one more time. So this time we're assuming that any epsilon positive taken away from S results in that new number being less than some element of A. That's our assumption, and we're going to prove from that S is the least upper bound of A. So if there is some number B that is strictly less than S, which makes their difference positive, right? S minus B is greater than 0. Then B is not an upper bound of A. Because S minus B is greater than 0, I can take it to be my epsilon value. So I plug it in for epsilon, and that results in something that has to be true based on our assumption, that B is less than A. Since B was less than S, and we showed that B was less than A, that means that any number less than s cannot be an upper bound of this set capital A, which means if b is an upper bound of A, then it must be greater than or equal to s, because anything less than s is not an upper bound of A. And therefore, if every upper bound of A is greater than or equal to this number s, that means that s is, in fact, the least upper bound or the supremum of A. So we have shown that to be true. QED, we've shown both directions. So we've been able to mold this new axiom of completeness with this for every positive number epsilon kind of argument, which is going to be ubiquitous throughout doing real analysis, because the idea is to try and get as close to something as you want and be able to derive the result that you want. So why talk about this, right? Why go through this axiom of completeness thing? How does this distinguish us? How does this distinguish the real numbers from the rational numbers? And it's not too hard to see how, because all we have to do is construct a set of rational numbers which does not have a least upper bound in the rational numbers. So I'm going to construct a set. So this is a set of rational numbers such that q squared is strictly less than 2. So this is all the fractions that are small enough that if you square them, they are less than 2. And so, of course, the number, if we were to say in the real numbers what all of these are less than or equal to, in the sense like the smallest number, of course the smallest number is the square root of 2, right? All elements of q are less than the square root of 2 for all little q in big Q, right? Where big Q is, of course, the rational numbers. So, of course, this is the case. This is true, and this would be the least upper bound if we were investigating it in the real numbers, but since we're only looking in the rational numbers, and we were able to show that this particular number is not in the rational numbers, right? It's not an element of the rational numbers, we know that this can't be a least upper bound in the rational numbers, right? So therefore, it's not always the case that every set that is bounded above in just the rational numbers has a least upper bound, because this least upper bound isn't even included in the rational numbers, so it doesn't work there. And so it really does genuinely distinguish the rational numbers from the real numbers, and it's a wonderful place to start because it allows us to fill in all of these little gaps, which you will find later that there are myriad gaps. Like, it's not just the case that most things are rational and there's a few numbers that are sort of disparately, placed about. There's really a lot. And so this distinction between the rational numbers and the real numbers, of every set that is bounded above having a least upper bound, really does distinguish the two. Because in this, just a single counterexample, we see that this set of rational numbers does not have a least upper bound in the set of rational numbers, because I can pick fractions that are progressively bigger and bigger, as long as they just stay small enough that their square is less than 2. Just like we could, in that open interval from 0 to 1, always find bigger elements, right? 0.9, 0.99, 0.999, right? We can always find bigger elements, but still everything in here is less than or equal to 1, and 1 is the smallest number that has that property. But again, that's the real numbers. This is just the rational numbers, and the square root of 2 is not in there. And so the axiom of completeness does not apply to the rational numbers, only to the real numbers, so far. Well, that's all we'll be saying about it applying to the real numbers in this series. So I hope that's clear. We really just need the axiom to distinguish what we mean by the rational numbers and the real numbers. So now we have to derive a couple more results that are quite easy. They sort of seem true on the face of it, but we'll sort of just prove them today just for posterity. So the first one is called the Archimedean property or principle. Median. I think that's how you spell that. Archimedean? Oh, no, it's Archimedean with an E. Okay, the Archimedean property. And this is two different claims. So one is that given some real number, x, there exists a natural number with x being strictly less than n, that natural number. And that's not too hard to see. This is just saying that the natural numbers are not bounded above, right? No matter what real number you pick, I can always find a natural number that's bigger than that. Of course, if you pick 0 or any negative number, that's very easy. We can just pick 1. But if you pick any positive real number, then I can just think of a bigger integer. I guess it should seem like it should go without proof, but let's just do it to see the argument. So assume that the natural numbers are bounded above, right? This will go to help proving this Archimedean property that we want. So assume that they're bounded above. So if they're bounded above, then there exists x, which is the supremum of the natural numbers, right? It's the least upper bound, which implies that n is less than or equal to x for all n in the natural numbers, right? There is some real number that's bigger than all the natural numbers. And since it's the least upper bound, we showed in the last proof that if I took any positive number away from x, it would be less than that element, than some element, right? So x minus 1 is then therefore less than some m, so some m in the natural numbers, so some integer, right? X minus 1 is less than that, but of course we can just add 1 to both sides, in which case we get x is less than m plus 1. But since we know that the natural numbers are closed under addition, right, the integer m plus the integer 1 is another integer, we know therefore that we have shown that the natural numbers are actually not bounded above, because we assumed that they were, said that therefore there must be some least upper bound, and then showed that that least upper bound is less than some element of the natural numbers, which is of course a contradiction. So the two arrows pointing at each other, contradiction. Therefore, the natural numbers are not bounded above, and therefore no matter what real number you pick, you can always find an integer that's bigger than that real number. And so now we're going to use this first part of the Archimedean property to prove the second. So given y in the real numbers, the positive real numbers, sorry, just the positive real numbers, then there exists an n, a little n in the natural numbers, with 1 over n being strictly less than y. Of course, this is also greater than 0 because every natural number is positive, so 1 over every natural number is also positive. And so this is easy to prove. All we have to do is take x to be 1 over y, right? That's our real number. We're going to consider our real number to be 1 over y. Then by the first property, then by 1, there exists n such that 1 over y is less than n, right? Because we proved the first part, which means that no matter what real number we have, in this case 1 over y, there's going to be an integer that's bigger than it. But by reciprocation, this implies that 1 over n is less than y, which proves the second claim. So we have the fact that no matter how big you pick a real number, there's always an integer bigger than it, and we say no matter how small you pick a positive real number, there's always the reciprocal of an integer that is less than that. And so that's the Archimedean property, and that's another thing we're going to need. So you should write that down if you're interested in keeping notes. I'm just sort of going through the proofs so far. I think that at the end of each chapter of the textbook, I'll go through some problems from each section and just upload those as the problem sets. I think I'd much rather just kind of go through and do the lessons first throughout these. And so next we have to prove the nested interval property. So the nested interval property is kind of a lovely little fact about the real numbers. So the nested interval property. And it states that, so say we have these nested sets. So we have I1 being a subset of I2, being a superset of I2, being a superset of I3, and these go forever. So we have infinitely nested subsets of real numbers, with In being the interval from AN to BN, and these are closed intervals. So all of these are closed intervals, and they are nested inside of one another. So an example of what this might look like is we have the real number line, and we have A1, B1, A2, B2, ... all the way down to AN, BN, and then of course they keep going in forever and ever. So they're nested intervals. That's the thing. And what we're going to prove is something quite fantastic about these things. We're going to prove that the intersection of all of these subsets, so the intersection of all of them, and what I mean by that is I'm going from n equals 1 to infinity of all the INs, and I'm intersecting them together. So I want to find every element that's in every set. So I want a collection of all the elements that appears in every single set. And the claim is that if these are nested closed intervals, that this infinite intersection will never be empty. There will always be at least one real number in the intersection of all of these sets. And I will prove that today. So how will we prove the fact that this intersection is never empty of all these infinitely nested closed intervals on the real number line? So let's do that. So let's take our assumptions to the proof. And so what do we want to do? We want to make A the set of all the ANs, which were the lower bounds of those intervals, right? The lower, the minimums, I guess you could say, of the sets because they were closed, and so the ANs are there. Notice that BK is an upper bound of A for all k in the natural numbers, right? because all the endpoints of the intervals, the bk's, are all bigger than all the starting points of all the intervals, right? So any of the endpoints, any of them are bigger than all of the starting points of every interval, right? Because they keep nesting in like this, and the upper bounds never get below the lower bounds of the intervals, and so they sort of move in like this. And so all the b's are always bigger than all the a's. So because that means that the set A of all the little starting points, an, is bounded above, which means in particular there exists a least upper bound for A. So let x equal the supremum of A, right? We know it's bounded above, and by the axiom of completeness there must be a least upper bound. So by the axiom of completeness, by the Alexandria Ocasio-Cortez, we can assume that there exists some x that is the supremum of A. So we know that it is greater than or equal to all the ANs, and we know that it is less than or equal to all the BNs. So we have that x is the supremum of A. So therefore there exists some supremum of all the ANs. But what did we sort of just say? We kind of made a fantastic little claim here. Because x is the supremum of A, it is therefore greater than or equal to all of the ANs. But because it is the least upper bound, and all of the BKs are upper bounds of the set A, x must therefore be less than or equal to all the BNs. So for all n inside of the natural numbers. That means that x is in every interval, every closed interval from AN to BN, which is the interval IN, right, by assumption. Which means that x is in every single is in every single interval. X is in all of them, which means it must be in the intersection of all of them. Because the intersection of a collection of sets, whether the collection is infinite or not, is just all the elements that appear in every set. Since we've just shown that x does appear in every one of these intervals, it must therefore be in the intersection of all of them, which proves the intersection of all of them is not empty, right? Which is the theorem, right? We showed that the nested interval property is true. So if you have an infinite nested collection of intervals that are closed, then the intersection of all of those intervals is never empty, and we just showed that because there's at least one element, which means that it cannot be empty. So I hope that's clear. We've just shown that the nested interval property holds. And so now that we've shown all of these things, we now have tools that we can use to prove some pretty fantastic results involving the real numbers. So we've only got a couple more results that I want to demonstrate in this round. So the first one that I want to demonstrate is that the rational numbers are dense in R. Now what does that mean? The rational numbers are dense in R. So what I'm saying is Q is dense in R. And that's what I mean by that is between any two real numbers, so given A and B elements of R and A not equal to B, so there is some difference between them. So we can assume that for the sake of simplicity that A is less than B, but of course it doesn't matter if B is less than A. Given this, then there exists a rational number, so we'll say Q. There exists that such that A is less than Q, which is less than B. So that's saying that for any two different real numbers, you will always be able to find a rational number between them. Remember, we showed that Q was dense in itself, because between any two rational numbers, we can always find a new rational number. But we don't, for example, know that there is not some collection of holes somewhere in the real numbers, right, that we needed to fill in by using the axiom of completeness. Maybe there's some interval where there just are no rational numbers, and then this doesn't hold. But it's actually not the case, and it's pretty easy to see how that would be. So what we want to do is we know that Q is some fraction, so we'll say m over n, right? It's two integers divided by each other. What we need to do is we need to be able to show that there has to be some rational number between any two real numbers. So what we need to do is we need to be very, very fine. We need to figure out an interval that we can add a bunch of times that's small enough that it doesn't overstep the interval from A to B. So what we're really trying to do here, another way of saying this, is that if we replace Q with m over n, we're actually trying to show that n times that real number A is less than the integer m is less than n times that integer b, because before it was A is less than m over n is less than b, I just multiplied all the sides by n. So these are the same statement. So we're trying to prove this statement right here, that no matter what A and B are, as long as they are different real numbers, then there is some rational number between them. That's what we're trying to show. And we're going to need to use the Archimedean principle for this. So since we assumed that B was greater than a, we know therefore that b minus a is positive, right? So we can take b minus a to be the y that we had when we proved the Archimedean principle and say, since b over a is greater than 0, then there exists some natural number n such that 1 over n is less than b minus a, right? We can find a big enough integer that if we reciprocate it, it's less than b minus a, which means that no matter how close together b minus a are, their difference is bigger than some reciprocal of a rational number. So we've shown that we can find a denominator that is small enough that we can add repeated, 1 over n plus 1 over n plus 1 over n as many times as we need it. It will land us between b and a, no matter how close b and a are to each other. Because we can always find a big enough integer that this will be small enough that we can have a fine enough resolution that we actually land between a and b. Also, because of this, we have effectively chosen our value for n, right? We don't explicitly know its number, but we know that it has the property that its reciprocal is less than the difference of a and b. Also by the Archimedean property, we can find an integer m with this property, that m minus 1 is less than or equal to n times a, which is less than or equal to m. Because remember, n times a is just some real number. By the Archimedean property, at least the first part of it, we can always find an integer that is strictly greater than that real number. And so that's going to be our m, and in particular we want it to be the smallest, which is to say that if we took 1 away, it would be less than or equal to n times a, which is to say not greater than. So by the fact that we can find an m that does this, this implies that a is less than m divided by n, which is the first part of our thing that we want to prove. So now we just have to show that b is strictly greater than m over n, and remember, m over n is just a rational number that we have shown to be between them without specifying what the values are, which means we will always be able to do it, and so it's a general proof. But now we have to prove the part with b. So the fact that we were able to know that this inequality has to be true for some n, we can actually rearrange that. So I'm going to erase this part here. We now have the first half. Remember, we have that a is less than our rational number. Now we just need to prove that b is bigger than our rational number. By this right here, we have that a is less than b minus 1 over n, right? So this is sort of like saying that we take away this really, really tiny real number, which is just the reciprocal of some large integer, away from b, and we still are bigger than a, right? So that means that our resolution is small enough that even taking away the reciprocal from b, we're still bigger than our number a. Utilizing the fact that m was the least integer that was bigger than n over a, we had this property, right? So we have that m minus 1 is less than or equal to n times a, right? Because we assumed that m was the smallest integer that we could pick that was strictly greater than n times a, which means we can just add the 1 over. Right, so this was just we could just add the 1 over, but now, since we know that a is strictly less than b minus 1 over n, we can say that this expression is strictly less than n times b minus 1 over n, we're just replacing a with b minus 1 over n, plus 1. But of course now we just distribute the n, and we see that this is equal to nb minus 1 plus 1, which is of course equal to nb, which proves that m is strictly less than n times b, which proves that, let's say that again, which proves that m is strictly less than n times b, which implies that m over n is strictly less than b, which was the second part of the property that we wanted to show. So we have now shown that our original real number a is less than some rational number, and we showed that our original upper bound b is greater than that same rational number, which means that no matter which two real numbers you pick, a and b, you can always, always, always find a rational number between those two numbers. Very cool. So the rational numbers are dense in Q. There are not what this tells us is that there are not these long stretches or any stretch at all of any length where there exist no rational numbers. It's not like there's these islands of all irrational numbers, right? No matter what two real numbers you pick that are as close together as you want, there will always be a fraction between them, and that's the conclusion of this proof here. So Q is dense in R. So by a similar argument, it's not too hard to see that you can prove that the irrational numbers are also dense in R, but I will leave that as an exercise, and perhaps I will cover that in the exercise video that I make regarding the entire chapter of this book that I'm going through when we get to the end of it. Okay, so I think that's actually enough for today. I think we've probably done enough. So let's review what we covered today. We covered the axiom of completeness. We covered the Archimedean property. We covered the nested interval property. We proved that the rationals are dense the set of the rational numbers, is dense in the set of the real numbers, which is to say that for every two real numbers that are not equal, there is some rational number between them. You should try to prove that the irrational numbers are also dense. And then one final thing is to actually prove that the square root of 2 belongs to the real number, so we actually have an example of an irrational number that we're confident of. We also showed some properties of, we talked about supremums, and then sort of by default infimums, because they're just the opposite, maximums, minimums, and then and this is all from talking about the axiom of completeness, as well as regular upper bounds and lower bounds. Of course, the infimum, minimum, and lower bounds are just the mirrors of the supremums, maximums, and upper bounds. So those are the things we talked about today. Thank you very much for watching. I know this is sort of long. I'll try to cut it down to less than an hour. And I'd like to once again thank you very much to the patrons who support this channel, the few of you that do it at the moment. I hope that other people decide to join them. So thanks again for watching. Stay tuned for the next chapter. And what I want to do now is, given that this has been, it's been a while since I've put out a video, I want to try and just do one video every weekend, right? One long video. I'm not going to try and do like the weekly shows like Wacky Calc Wednesday or anything like that anymore. It's just sort of not really in the cards right now, given the two jobs that I'm working and all that time is kind of taken up. Plus I have a dog to take care of now. So I'm going to try and limit it to like one a week. I'm going to film them on Friday, edit them on Saturday, then they go up on Sunday. That's going to be like my goal, to just kind of get through these lessons on these subjects, and we'll see how that pans out. So once again, thank you for watching. Have a wonderful day.